This is Dr. Holt. I'm going to go over this pendulum problem here. I have a pendulum that consists of a 2.2 kilogram bob attached to a light 2.8 meter long string. While hanging at rest with the string vertical, the bob is struck with a sharp horizontal blow, giving a horizontal velocity of 4.7 meters per second. At that instant, the string makes an angle of 29 degrees. With the vertical, calculate the following. We want to find out what the speed is. We also want to find the gravitational potential energy relative to the value. Relative to its value is at the lowest point, the tension of the string, and what is the angle of the string with the vertical when the bob reaches the highest or the greatest height. Alright, I'm going to come down here. I'm going to draw a picture of kind of what's taking place here. I will come here. I will grab a mass here like this. I will have a string come up like this. Okay, now I'll bring this over here. Go ahead and clone this. We'll make this, fill this in so you can see it. Okay, now this one is going to have a velocity to the right, and I'll draw that with a vector. And the velocity up here is going to be given as 4.7 meters a second. So I'll make this 4.7 meters per second. Okay, now this bob is going to swing up. So I'm going to kind of try to draw like a rough arc. Here like this. And I'll color that. Make it thinner and dot like that. Alright. Again, I must try to move this down so it's not interfering with all the text here. We'll grab this. We'll move it down here. Okay. And let's erase this right here. Okay, now what's going to happen is it's going to swing up. So I'm going to bring this guy up here. Going to bring up here at some point, and it's still going to have some type of velocity. We don't really know what that is. And now it says in the problem that the angle in the vertical is 29 degrees. So we know this is 29 degrees. We know the string is going to be 2.8 meters long, and we know the bob has a mass of 2.2 kilograms. Okay, what I like to do is I'll draw a horizontal line here. I'm going to take all my gravitational potential relative to this point, so I'll let this be my neutral axis. Okay, now we'll write our equations, and we can say this will be position 1. And this will be position 2. So I write out the potential energy of gravity at 1 plus the plus the kinetic energy at 1. And I'll put in work done by non-conservative force, and we know there's not going to be friction, so that's going to be equal to 0. Is going to equal to the potential energy gravitation at 2 plus the kinetic energy. I'll make that K better. Plus the kinetic energy at 2. Alright, let's label what we know as 0. If this is where we're going to start, this on neutral axis, then our potential energy gravitation be 0 here. We have no work done by non-conservative forces here. This goes to 0. Now when I get up to here, I'm going to have gravitational potential and kinetic energy. Alright, so we write out over here what the kinetic energy has. Get rid of this real quick. Let's just shift this. Okay, that's going to give me 1/2 times my mass, and the bob has a mass of 2.2 kilograms, times my velocity squared, which will be 4.7 meters per second. We will square that. Okay, that's everything I'm going to have on the left side, and then equal here, And now the gravitational potential. Now this, you got to think about this just a little bit. We need to know what is the distance right here. We need to know what is this distance from here to here. I'm sorry, my arrow's not very good. That's vertical distance here. Now, isn't that distance going to be the length of this, which is going to be 2.8, minus 2.8 times the cosine of 29? Again, let me repeat that. The distance from here to here is 2.8. The distance from here to here is 2.8 times cosine of 29. So I just need to subtract those. So I'll write out the mass, 2.2 kilograms, times acceleration of gravity, 9.8 meters per second squared, times that distance, which will be 2.8 minus 2.8 times the cosine of 29 degrees. That's me, my gravitational, plus the kinetic energy I have, which will be 1/2 times 2.2 kilograms times the velocity I'll have at 2 squared. Now if it's me, I would go ahead and cancel out the masses. I can cancel out here, here, and here. Alright, now all I have to do is solve for my velocity right here. And when I do that, I will start rewriting this. And I will have 1/2. Let me do that in black. I'll have that 1/2 times 4.7 meters per second squared. Okay, I'm going to simplify this side over here. First thing I'm going to do is see what we can do with the 9.8. We'll simplify this. We'll have 9.8. I will go ahead and pull out a 2.8. Actually, we'll do the math. We'll just leave it like that. It doesn't matter. V2 squared. Now, I'm going to go ahead and move this to the other side. So to do that, I will subtract all this. I'll just take the equal sign here. I'll take it out. I'll make this minus here. I'll have my equal sign here. Okay, and now all I have to do is solve for V. I can do the algebra, and when I do that, I will get V2 as 3.9 meters per second. And go back and you'll check that answer right there. And exactly what I got. Okay, now it said here, what's the gravitational potential energy relative to its value is at the lowest point. I don't like how they said that, but that's what they're looking for. We want to find what is the gravitational potential energy relative to this. Well, really, it's going to be all this right here. So my gravitational potential relative to that point is just going to be the 2.2 kilograms times 9.8 meters per second squared times 2.8 minus 2.8 cosine 29 degrees. And when I run that, I get 7.57 joules. Again, that is the gravitational potential energy of the bob at this position, 29 degrees of the vertical relative to this point down here. Now the other question says, what is the tension of the string? To find the tension of the string, you need to draw a free body diagram of what's taking place when I'm at the 29 degrees. And I'll come down here and I'll do that. So I have my bob sitting here. I'll draw a picture and then draw the free body diagram. I have the bob sitting here. The string is going up here like this. Okay, so we're going to make that's going to be our tension. Like that. Again, we know this angle here is given as 29 degrees. Okay, so now I'm going to draw a free body diagram of this, and we know this is 2.2 kilograms. So I come over here. I will draw this straight down here. Oh, let me get a vector. Like that. That's going to be my force of gravity. And that's going to equal to 2.2 kilograms times 9.8 meters per second squared. All right. From that point there, I will draw what else I got taking place, and the only thing else I'm going to have is my tension coming up here. This is my tension. Again, we know this is 29 degrees, so alright, so if that is 29 degrees coming off the vertical here, then we know that this angle right here has got to also be 29 degrees right here. That's 29 degrees also. Alright, so now I go back just to prove that. Now the only other thing, since this thing has velocity, it's going around, I have acceleration back toward the center. And this is going to be mass times centripetal acceleration. What I'm going to do at this point is I'm going to establish this as just the x-axis going this direction here. Now I'm going to sum the forces in the x direction, and I'm going to set it equal to mass times my centripetal acceleration, which is also going to be in the x direction. When I do that, I know this one I need to break in components. So remember, again, if this is 29 degrees, this angle here is 29 degrees. So I'm going to let anything that goes up be positive, anything that goes this way be negative. So I'll get negative 2.2 kilograms times 9.8 meters per second squared times the cosine of 29 degrees. Plus my tension must equal to my mass times my velocity squared, and what did we say the velocity was? 3.9. Divided by the radius. Okay, again, I'm just doing mass times velocity squared divided by r, because that is the value of the centripetal acceleration as they go around, and it's always pointed inward because the velocity is moving, the velocity is changing as I go up. So now I have to do is move this back over. If I take all this and multiply it by the cosine 29, move it back over here and add to that, I will get my tension as equal to 30.8 newtons. And let's check to make sure that is correct, and that is what I'm getting there. Alright, now what is the angle of the string with the vertical when the bob reaches the greatest height? Alright, when the bob reaches the greatest height, then this velocity is going to go to 0. So to demonstrate what I mean is, someplace up here this bob is going to reach a certain level. Let's clone it. Change it, make it blue. Again, and the velocity here is stopped. And I'll draw the vector. But this velocity is equal to 0. I've reached my maximum height. So really what I need to do is I need to draw the line. I need to find out what is this angle right through here. So I go back. Again, it's just the simple energy equation. And I write down how much. Again, I'm taking all all my gravitational potential energies relative to this point here, my neutral axis. So again, all I'm going to have is kinetic energy down at that point. So I'll write all the equations down. I'm just basically going to do this. Gravitation potential G that I'm going to have plus my kinetic energy I have at 1 plus the work done by non-conservative forces, and again we know that is 0 because there's no friction taking place, is equal to the potential energy, gravitation, and we'll say that's at the position 3, plus the kinetic energy at 3. Again, it's come to a stop, so this is going to be 0 here. Now, since I'm taking this at the bottom, this is also going to be 0. So all I'm going to have here is going to be 1/2 times 2.2 kilograms times my velocity, which I believe was 4.7 meters per second. I'm going to square that, is equal to my mass, 2.2 kilograms times 9.8 meters per second squared times 2.8 minus 2.8 times the cosine of theta, because I don't know the angle at this time. Again, it was me. I'd cancel out the kilograms here. Now I'm ready to solve. I'm going to move everything over to the other side. And then, am I not going to get 4.7 meters per second squared over 2 times 9.8 meters per second squared. On this side here, I will pull greatest common out, which will be 2.8 meters. I should put the units on there, meters, over 1 minus cosine theta. Okay, I'll bring the 2.8 over, and then I'll subtract by 1, then I will take the inverse cosine of that value. And when I do that, I will get theta as equal to 53.3 degrees. Now again, if you're a little confused about the math, let me just clarify how I'm doing that. Okay, I'm going to move the 2.8 down to here. So now I'm down to this point here. Okay, now I'm going to subtract 1 from both sides. So I'll move this over here. And that's going to equal to the negative cosine. Now I will negate everything. So this will become negative all over here. This will become positive here. This becomes positive here. At that point, I take the inverse cosine of all this. And then when I do that, I will get theta is equal to 53.3 degrees. Alright. I hope this video was useful. Again, I solved 4 different items here. I found out what the speed was when I'm at an angle of 29 degrees relative to the vertical. I found out what my gravitational potential energy is when I'm at 29 degrees. I found out what the tension in the string was, and I also found out the angle when I reached maximum height. Right, again, best of luck with these type of problems.